First of all, I want to make sure the projects are ongoing, right? You are not waiting for the next week to get started. I hope not. Right, because it is going to be a substantial thing, given that we don't have finals and midterms. And the second thing that I don't want to see a situation where there is this Superman in the group who can take care of everything, and everyone else get a free ride. This is fine in some situation, but in our case, I do want to see everybody had a chance to present and to show an understanding of the project. So in the final presentation, which is oral, I'm going to ask everyone in the group to split, the time slot, okay, to do a presentation. Of course, you can choose to be in the intro, in the methodology, in the results. That's up to you. It's really up to your taste and preference. But at least you need to have the equal slot to speak. Okay, that's one thing. And the second thing which happened in the past is that some people, in fact many people, wants to talk more because they have so many exciting results. But unfortunately, we have very limited slots. So I'm going to enforce every talk to be given a very, very limited slot. I don't know the time slot yet. It might be 10 minutes, maybe a little bit shorter or longer. And at the end of that slot, you know what's going to happen? There will be some animal barking at you, and you'll be dragged away from the podium, okay? This is a rule not invented by me. It's invented by our department chair, who used to teach us how to stay on time in our faculty presentations. I'm going to apply that to you guys. Right? So don't blame me that I'm too brutal on that, but we do want to stay on time. There will be snacks, refreshments, stuff like that, so that you can relax. But make sure you will be, in that mini symposium. And we will also decide whether we need to have a poster or not. Sometimes maybe that time is just too short for you to show everything. Maybe we will get a poster at some point. You can have more time to showcase your results. But so some details will be announced either later this week or early next week. Okay. All right. And also another announcement. I try to be really teaching all the lectures myself, for the entire semester. But finally, I decided I couldn't do it this Wednesday. I had to go to Iceland for a conference, and I cannot be back on Friday. So I asked certain members in my group to guest lecture a class, okay, which will be a very important one. It is going to be the distributed MCMC. That people are talking about big learning and stuff like that, and one key component is to do probabilistic inference in a distributed system. So in fact, it's not as simple as just loading your program into a cluster and kick the return and see everything happen. You need to redevise the algorithm, if not the system itself. So you are going to see some research ideas along that line. Okay, so please show up on Wednesday to see that talk. Hopefully, they will be doing a better job than I do in explaining that, because many of the work are their own research projects. All right, so today we are going to continue what we started last week on using the graph to now drive or inspire structured sparsities, okay, in certain functional estimation. And last time, the only type of functional estimation we talked about is on what functions, if you remember. Do you still remember that? We were talking about a very simple function like this, right? It's literally about something like that, right? So it is a very simple linear function, which is okay, for pure intellectual purpose. But if you are interested in a real-world application, very often this particular function is not powerful enough. So today we are going to go to the real world and see some more powerful thing. Oddly enough, even though people know this is not powerful enough, this is probably the major practice in 99.99% of the community I know of. Even in finance industry where you put billions of dollars onto your trading, people probably are using this. So I guarantee you can gain a lot more if you are willing to step one little step out and try something what we talk about today. All right, so that's the plan of the talk, of the lecture, and let's just move on. So we start by, revisiting some of the ideas in nonparametric kernel, functions and regressions. So here is the setup, right? So we saw this kind of graph already many times. You have dots here and there, and so far with this functional, your goal is to find a line, right, which is linear, and then you are going to estimate the beta, which in this two-dimensional case translates to the slope, and if it's a high-dimensional thing, it's a vector. And so obviously there will be many points which are not falling onto the line, and you are minimizing the least square error of that. And today we are going to talk about maybe how about try that, or maybe to basically visit every point like this. Okay, so how to achieve that? And usually this force you to visit a technique known as nonlinear functions, and the simplest one is the following. Okay, you are going to still use the main ideas under linear regression, except now that you are going to replace the original x, okay, with some transformations of x, some function of x, okay, but they are still linear combinations of this function, and you get y. And the linearity is achieved by manipulating this phi function, right? For example, this phi can be a polynomial of multiple orders, right? And then your little functional here is just a vector, and you have all these different orders, and then you get a linear combinations of that. And because the terms itself become nonlinear, then you get a nonlinear fit, right? And of course, you can see originally you have one-dimensional data, and now you artificially push them into a higher dimensional, and that creates a need, for example, to remove some of the redundancies. And also here, the results can be a little bit trickier because these different dimensionals are not independent of each other, right? They are coming from the same dimension. You just square it and cubic it. So that's going to create dependent dimensions. And many of the proofs that people see in lasso regression and so on will break down because the convergence guarantee or the consistency guarantee of sparse regression began by an assumption that all the input dimension has to be independent of each other, right? So this is doable. It's not necessarily the best idea, but we're going to pursue this direction a little bit further, see how we can make things better. The first thing that you can do to make this happen is to choose different functionals, right? So there are a collection of choices, and we now are going to revisit this idea of kernels. Right? There are different little kernel functions: polynomial, radial-based kernel, sigmoid, everything. Each of them can provide you a nonlinear basis. It doesn't change anything in your regression practice. You just estimate the theta. These functionals are provided as your design choice. Okay. So here is just an example. Now you have this one-dimensional regression. It looks like a three-dimensional regression, but it's actually a one-dimensional regression because your input is only one x to y, right? And you are going to now plug in these sinusoidal curves. Okay, actually not. These are just three little Gaussian bumps. Okay, and you put beta 1 to 3 here, and then at the end of your fit, maybe you get the first beta being 2, the second being half, 0.05, and the third one being half. Then in combination, you have this red curve, which is the whole thing. That achieves you a highly nonlinear fit. And things become a little more complicated if you are doing high-dimensional regression, where the input itself is x1 to 3. Then you need to carefully index it. Okay, every x1 to 3 is now subject to another collection of a kernel transformation, and then you are going to blow up the dimensionality a lot. there is one choice you can make to basically adjust the effectiveness of this little kernel function. And this is a typical example which gives you the wisdom of how you might be doing a good choice. Right? So say we are now in the two-dimensional world. Okay, we have x1 and x2. Then your natural kernel will be a radial-based kernel, right, defined on the data points. And this is one choice, and that's one choice. And you probably can tell me, whether they are, good or not in this case, right? So in this case, the kernel is such that they are tightly defined around the points, and the 2 points are not touching each other. Therefore, there are spaces in the middle which are not really taken care of by any mass. Okay. Therefore, if I have points falling into here, for example, I don't really know, how to extrapolate from my existing points. That's usually a bad idea, right? And here, things go the opposite. The circle, basically the kernel function defined on points are way too wide. Therefore, if you pick any points in here or here, you'll see a whole lot of influences from all other points. Okay, that's mathematically okay, but interpretationally, you fail to draw a clean connection of which points are more important. And also, it tends to give you a chance to overfit because you just have so much degree of freedom. Therefore, you can just manipulate the number to make every point nicely fitted, but not necessarily going well for a new training point. Then, there is always this trade-off, to choose a reasonably wide kernel so that you touch every region, but not too excessively with overlapping influences from different points. Okay, so we probably see this before already, and I think in all these problems you have experienced, or at least probably expected this kind of underfitting or overfitting kind of trade-offs, right? So here, say I have a few points. I have a linear regression function. I have a second-order polynomial. I have a fifth-order polynomial. And I guess now we have no problem picking which one is better. Which one is better? The one in the middle is better, right? And this one, the function is not powerful enough to catch all the subtlety. This one, the function is simply too powerful to remember all the data points, but not necessarily generalize well to new points, right? So this one gives you a reasonable trade-off in the middle. And technically, we call such behavior a bias and a variance trade-off. So I'm not going to discuss this excessively because we at least see this notion twice in 701 and 702. And so the point here I want to make is that you need to, basically now, seek a nice trade-off between choosing very rich functions, to capture, regularities or patterns in the data, but also cleverly shrink them or control their complexity to avoid overfitting. Okay. So how to do that? At least from last lecture, we knew that in linear regression, we can choose the basis to be very high dimensional, and then we can add a structure sparsity to impose shrinkage, right? So now I ask, can we do this in the functional space? Okay, so that's basically a very simple extension from what we did last time. So before I show you the overall framework, I want to now make one step further to turn our regression framework from a parametric one into a non-parametric one, so that all the technique we talk about today can be grounded. So this is our linear regression, which is a fitness reduction type of optimization problem. So at the end of the day, you solve this estimator, which minimizes the square error, and you get a single estimator theta, right? So look at this one and this one. There is a subtle difference. So in this regression function, which is what we learned before, we are going to define the error by treating all the training points equally, right? Each training point xi is going to contribute a term, then you sum over all the n data points. In here, I very subtly add a weight on every data point, wi, which is meant to give you a chance to say, to basically impose, different importance of the training points, and why that's going to be something desirable. So look at this plot. So suppose that in addition to knowing the training points, I also know my query. Say my query comes from here. Okay. My query comes from here, and I also know I'm going to use a regression function to predict where this query corresponds to, in terms of its prediction. So now I ask, does this extra piece of knowledge change the way you are going to train your model? Yes. It should, right? Because if you already know that the query happens here, then you probably don't want to pay too much attention to the points which are away from here, right? At least you don't want to pay attention in a way that if I want to, for example, say I have a point in here which is really offline, and I want to try so hard to make it a good fit to the point that I need to change my curve, so that I actually end up with a bad fit in here, okay? But overall, you can see the fitting error is reduced because this one, after all, is online, and that one is not off by too far. But therefore, actually costs you a better fit than the original one. But on this particular region, it may not be as good. But the region that is not good is the region you really care about, because that's where you'll find your query, right? So that's why people reinvented this technique called locally weighted linear regression, which actually gives you the flavor of a nonparametric extension of a parametric technique. Okay. Now I'm going to ask, where my query point is, and then I'm going to design a weight accordingly to penalize or to weight every training data point. So it doesn't change the overall term. At the end of it, you still get a theta. Okay, but this theta is not going to be a fixed constant. It is going to be dependent on you plug in query x. Okay, and if I have another query x in here, what are you going to do? You have to re-estimate it, right? And then you are going to hopefully recalculate a prediction. So in that sense, you cannot just throw away all these training data points xi, right? In here, what you do is you get a optimum theta star estimation. Once you have the theta star, you throw away your data, right? That's the only thing left, and then you are going to make prediction. But in here, you are going to actually remember a weighting scheme, and also save all the data points for a potential reweighted estimation. Okay, and that's what we called a nonparametric statistic. Basically, the model is going to grow with your data, okay, and the number of parameters needed for that model is going to be a function of the amount of the data. You may notice that this is very similar to some technique such as k-nearest neighbor, where your decision, which is the label of the incoming point, is going to be decided on the fly, by looking at the neighboring points and look at what their labels are, and then do a vote, right? So in that regard, you need to also save all the training data points before you can, implement this technique. Can someone name yet another type of machine learning methods which have some kind of flavor in here? Mean shift. What is that?
Nonparametric density estimation.
Okay. Okay. Any more? Try something fancier. So here, basically, I'm not trying to point you to a technique of, say, remembering your data and reweight it. Reweighting is a good idea for nonparametric machine learning, but are there other things which bear the same flavor, meaning that you don't somehow find a terminal kind of representation, okay, due to various reasons, but you are going to wait for the results to actually, the query to actually come, and then cook up the, the solution on the fly.
Evolving network.
Mm-hmm.
In your previous slide, evolving network.
Evolving network?
In graphical lasso.
In graphical lasso. I don't feel.
You have an evolving network, then you have a weight based on the closeness, like the voting.
Okay.
Yeah.
You can make a case for that. Okay, let me push one more time. That's not the best thing I'm looking for, at least in this context. How about the kernels, the SVM and the kernel graphic models, everything like that? Have you thought about that? Remember that we often say, in a RKH reproducing kernel Hilbert space representation, the feature map is actually infinite dimensional. We actually don't know how to save that, right? Therefore, we couldn't really build a feature map or any operators and stuff like that. We have an abstract operator, and that's basically a kernel function where here's a dot, and here is my anchor point. And you can only compute it once your query comes in here and build a quick kernel. And that's basically translates to the dot product of two infinite dimensional vectors. But you don't see that infinite dimensional vector for each of them explicitly. Right? So that's basically what's very interesting for the nonparametric technique. It's really not only training point dependent, but also sometimes query dependent. And then you cook up a fresh dish on the fly rather than you made it and put it in the fridge and the second day you take it out. Okay, so it's a very different flavor. And of course, intrinsically, it is more costly, at least on the test phase, because you need to cook it. But it sometimes can be very powerful. Okay. All right. So here I have a slice summarizing the comparison between the parametric and the nonparametric technique, and much of which was already discussed in my previous presentation. And now let's push along this line and see how nonparametric model is used for fitting nonlinear regressions. Okay, and here you can see the kind of the examples and also their trade-offs. Okay, so here I want to begin by doing a slight kind of paradigm shift on the mathematical side to get you become useful to the use of operators, okay, rather than concrete algebra. This is more like a symbolic algebra that you want to know. So in here we have the linear regression function or parametric regression function, and your goal is to basically estimate a theta star, right? What does this correspond to? Well, this function usually can be interpreted probabilistically as by a conditional distribution of y given x, right? That's basically what this whole thing is about, because your noise is Gaussian. And then estimating, this, if we assume a parametric model, that means, the noise is Gaussian, then this is basically a Gaussian distribution, right? Therefore, for Gaussian distribution, what do we mean by estimating a regression? We estimate the mean and the variance of this, right? Therefore, we're going to somehow estimate y of x, okay, and maybe a higher order moment of that. That's essentially what we're doing, even though in here this one translates to that. Okay, so. But this is really highly dependent on our parametric assumption. First of all, we know that this conditional expectation on y given x, is a mean under Gaussian distribution. And then, we actually have the dimensions and everything set up. Therefore, we can, equivalently do this estimator. And we actually even have a normal equation for that, right? So theta star equals to what? Something like that, right? Now let's go into, let me tell you how to use this trick to move into a nonparametric regime, right? So our goal is to get an estimate of that. I don't assume any parametric form. Instead, I'm replacing them with a function. Okay, therefore, I call this a function of x. Okay, this is m. Okay, so this is what we call a regression function. And our goal is to estimate that. And this function could be anything. Okay, could be a infinite dimensional kind of feature vector in some space, or it could be just an arbitrary function of nonlinear nature, and so on. So let's see how this can be estimated. Okay, and here are our training data points. So the first assumption could be that let's just define this function to be a kernel estimator, because it has to be built on all these training data points. Okay, then I'm going to just make this assumption that this function, which is the conditional mean of y given the x, is going to be, a linear combination of all the y's in the training data, okay, weighted by some kernels. Okay, and this is called the Nadaraya-Watson kernel density estimator. Okay, just by choice. Okay. And here you need to estimate the bandwidth. So this kind of makes sense, right? You are making a prediction of the y conditioning on the x, and now you have a bunch of training x all the way to m, okay, and they go with all the y's as well, and then you are going to assume that this y, okay, which is based on a expectation, is going to be a weighted sum of all these y's, and the weight is defined by this kernel function. Okay. All right, so we call this a kernel smoother, okay, and the kernel smoothers must have the following property. It should be normalizable, okay. It should be properly centered, and it should have a positive variance. Okay, and this is just to make sure that they behave nicely and identifiable. And then, depending on the different bandwidth, you can basically adjust how much degree of freedom, or how likely are going to overfit the data, just like the circles that we visited before. So now my goal is to use this as an inspiration to design, a conditional expectation operator that we are going to reuse down the road for other choice of the regression functions. Okay. In fact, here I'm putting down already a more general form known as the linear smoother. Basically, the linear smoother only assumes that my function, okay, which represents the expectation of y under a conditional distribution of y given x, is going to be a linear combination of the y, okay, all the training y's, okay, and here is the form in linear algebraic form, and then here is just one example that we see before, okay. So this kernel smoother is actually an example of the linear smoother, okay. And they have, we have some other examples in here. You can hopefully go back and make the connection. And therefore, this is basically my expectation of y is now represented as a lambda, a linear transformation of the y. This y, by the way, is my training data. Get that? Okay. So if you are not very comfortable or familiar with this, you should actually now recall yourself, our parametric estimator of linear regression. So this is the normal equation where we estimate the theta. And in this setting, y equals to what? Y equals to theta, a new x. I plug in x, right? And if I put in here, that basically corresponds to what? Correspond to xt x minus 1 to 0 inverse and xt, and then this training x and y. And you can essentially see the connection from here to here already, right? So this corresponds to this, right? And this part, which actually had your plug-in x, is actually this yx. It's just a fixed form, okay, of your now linear smoother. In this case, it is already reduced because you are solely reliant on the design matrix, the training data, without any kernel smoother or any other manipulations. But I want to just make the argument that even in your parametric regression, your prediction of the y is actually a linear combination of all your training y's. Okay, so here is just a more fancy way of building a stronger such linear combinations. Okay. All right. So now we are getting down to this very generic, I would also call it a normal equation. Yes?
So you say it's the expectation of y. Is it that because you have the assumption that it's a Gaussian noise?
No, I just say expectation. I didn't say any Gaussian noise, right? I basically say here you are going to have a p of y, right? And if you have a distribution, for example, and you want to use a distribution to make a single prediction, what do you predict? It's an expectation, right? Almost by just without a blink, you will predict as an expectation. Therefore, we are going from here to here, like expectation of y given x. That's basically giving you the best prediction of y, right? And we call this whole thing a m of x. And in here, I never assume it is a Gaussian or any form. I basically view it as a non-parametric thing.
But you do have proof that it is the expectation. I mean,
what do you mean by proof? I choose it to be the expectation. Oh. I choose to predict y using the expectation. Therefore, now I'm basically computing the expectation.
Yeah. I'm just not sure why sy can be the you know it is the expectation of y.
I didn't see your. Can you repeat your question?
Because if you want to calculate the expectation, then you must follow the distribution.
Yeah.
You take the.
I did.
Integral.
Yeah.
So.
I did. I basically assume that this is a non-parametric form of that. I assume it is an unknown function. Right. Okay. Right. Originally, if you are Gaussian, this one just goes to as a mu, right?
Oh, you have a sum. You have a sum of all the data points. So
yeah.
That's why you are taking.
Yeah. Okay. It's totally non-parametric. Okay. So remember, I have the normal equation in here, and now I have a more like a functional normal equation. I basically say that this y prediction is going to be a linear smooth transformation of the training y. Okay. So this S is called a smoother matrix, and the smoother matrix is pretty obvious as we defined before. It is going to be a matrix where every row is basically this a list of little bases defined on every training point. Okay, and of course every column is every prediction point that you want to make prediction on. Clear about that? And then we say that this one is just a functional expression of this conditional expectation computation. Therefore, we basically can call this a operator. Okay, so this one equals to a p operated on y. Okay, so whenever now you see that I need to have a conditional expectation over y, which can be written in here, what you can write is that it is going to be this. Okay. All right. So this is actually our very kind of subtle change of notation. We are going to now replace this one with this side. Now we are going to actually apply the technique to the true nonparametric regressions. And there are a few models that we are going to do. And we are going to start with the simplest one, the additive model. So originally, we basically assume that m equals to what? M equals to maybe a bunch of, it's basically a function over x, right? Mx is basically a function of x. And the function is defined on training data points. For example, I equals to 1 to p to n, and these are training points. And of course, I have my argument x in here. That's something like that, right? This is our original nonparametric definition of the function. The problem with this is that this type of smoother or smoothing functions tend to break down in very high dimensional space. This is a little bit hard to imagine, to see directly, but you should develop this nice intuition. Okay, in a very high dimensional space, this definition of Euclidean neighborhood basically breaks down. Okay, even if you might appear to be very similar or very close to a particular point defined by Euclidean norm, you are not necessarily very close. Okay, therefore, if you just plug in high-dimensional data using a Gaussian kernel, you're going to get a very poor fit. So the next kind of idea is to replace this one with a additive model, where I'm going to define on every dimension a kernel. Okay, so this is defined on every dimension. And remember, this J index is not the data index; it is the dimension index. Okay. And of course, the kernel, if I define in this way, will give me some little technical trouble because they may be non-identifiable. If I add one dimension, a constant, and subtract the same thing from another dimension, then they give me the same fit. That's going to cause the f to be non-identifiable. Therefore, I need to center the x. Okay, so that's a additive model. Additive model is basically by design. I just choose the m. Okay, this smoothing function to be like that. Okay, and then how to actually now estimate, okay, such a function, and also this intersect. Okay, now this is our loss function. Okay, I'm going to minimize the fitness error, okay, of the predictor and the training data. And how to do this minimization? Well, if you replace this with theta x, you all know how to do that, right? You take a derivative with respect to alpha with respect to theta, you get the theta estimation. Now it is no longer this, it is that, and you pretty much use the same mathematics, okay? And you can take a variational derivative of this whole thing with respect to a function. And if you want, you can do some exercise on the back of your envelope. At the end of the day, you will get these two estimators. The alpha is going to take the value as the expectation of y, and every base fi is going to be this. Okay, it is the conditional expectation of this thing. This thing is basically, you can call it a partial residual. Okay, it's called partial residual because it is the target, and this is the prediction made by everything but one component, which is j. Okay, so this is the partial residual with respect to dimension j, and you take an expectation of this guy using the conditional distribution of y given x, xj of that dimension only. Remember, this is by per dimension. Okay. Okay, and so this is something that may appear a little bit mysterious, right? And but remember, we already invented a few operators. We know that this guy can be written as a p of x, right? P being the conditional expectation operator, right? So Actually, this time P applies to that dimension only because we are now having an additive model. Therefore, here you have an additive sum of every dimension. And they don't interfere with each other. Therefore, when you take a derivative, they separates. Okay? Okay, so that's the equation in here. So how can we turn this derivation into an algorithm? Okay, that's our next problem. So here's the algorithm. It's called backfitting. You start by estimating the alpha first, okay, which is exactly the sample version. This is a population version of the results, right? You take an expectation, but now what you are having is a training set. It's a sample, right? So you replace this by a sample version. Therefore, the alpha equals to the mean of the sample mean of the y's. And here, it's a fixed point iteration, right? You see f on both sides of the story, and every f is going to make use of other f that is estimated in a different round. But you have this conditional expectation operator, which we already derived earlier that it is equivalent to applying a smoothing matrix S, right? All right, so then that becomes clear. Then for every dimension, you are going to now plug in on the right-hand side this residual, partial residual, and multiplied by the smoothing the smoothing matrix, okay? And then the smoothing matrix is what? It's actually computed by, if you remember. Yeah, it is basically, do I remember that? Yeah, okay. It is the basically it's the evaluation of the regression function on that particular point, on every training point, right? So you're going to basically, and to get this is what? This is basically, all this, kernel-based dimensionality, dimension-specific kernels, and they need to add together, right? So you need to provide this S and estimate the F. And then remember, we want to achieve identifiability by making all the F centered. So we need to center it. And then you go back to this iteration and redo the estimation of the F. And also reevaluate the S. And at the end of the day, they will stabilize at a particular fixed point. Okay? So this is almost like a coordinate descent algorithm. You are basically treating every function as a coordinate, and then you are going to iteratively update every coordinate. So this algorithm is called backfitting. And it's almost the same as your coordinate descent algorithm for linear regression, except now that your each theta is now replaced by a functional, okay, in your nonparametric design. Okay, any question on this? So with this algorithm, what you can achieve is to perform, now nonlinear fitting. And you can actually now, this is just a showcase of the results. You have a data set which correspond to, a response as a function of 3 inputs in nonlinear fashion. And here, after the backfitting algorithm, you can correctly get you can see that the function is indeed a nonlinear form of that. All right, so that basically is the the starting point of nonparametric regression, and then we are now talking about how to add structural sparsities on that. The first advancement actually happened in here, okay, or by John Lafferty and his student. They invent a model called sparse additive model, which is to ask the following question. So suppose that you have a small training data set, okay, with n, and your p, which is the dimension, is very big, okay. And this is a familiar scenario in Lasso, and we know how to do that, right? In Lasso, we are going to do this we're going to do this estimator, where this one is performing the function of shrinking the unimportant theta. And now we are no longer doing the nonlinear regression, the parametric regression. We are in the nonparametric space. So similarly, you have this loss function now, okay? And then you have to now seek a sparsity in the functional space, okay? And here is a direct kind of a borrowing of this formulation. You're going to now assume that the expectation of every function, okay, square root of that, gets a L1 penalty, okay? All right, so that's basically called the sparse additive model. How to actually derive the solution to that. So with all the preparations we had before, such as the linear smoother, the conditional expectation operator, now the derivation become very symbolic. You basically replace whatever you found to be hard to compute by a abstract operator, and here is one example. So remember that without a shrinkage function, our estimator was this one, right? And now with a shrinkage function which penalizes small functionals, we're going to introduce an algorithm called soft thresholding, okay, which has this form. This actually can be just directly derived by taking a partial derivative of this with respect to this. And what it says is that if this term is big enough, then it will generate what? A pretty substantial positive numbers in here. Okay, and therefore this one will be kept, okay, if this one is big. If this term is very small, what does it mean? It means that this functional is a residual that is not having a lot of influence. Then this term will be very big, and 1 minus that will either be, will be probably negative, right? If it is negative, then we just keep it as 0. Okay, so that's basically called soft thresholding. Okay. So by this particular penalty, we're going to have a way to remove many of the small functionals f, just as what we did in the lasso regression. We removed the theta. It is achieved by the same technology. Okay. And then everything goes the same as before. You have this now new updated equation. Okay, and every time you are going to recompute the residual and also the smoothing matrix, and then you iteratively update every function. Okay, and that gives you a sparse estimation of the additive model. Any question with this algorithm? Quite mechanical, right? And basically you replace this conditional expectation P with this matrix, and that's how things carry through. And this S matrix is already defined before, which is the sample estimation of the regressional prediction.
So this is compared with the back-fitting algorithm we just discussed. We only have the
yes, with the soft thresholding.
So that thing means if the thing in the if it is larger than 0, then just keep it as this. If it is smaller than 0, then Fi is 0.
Mm-hmm. Yeah, that's how you achieve feature selection. That's the algorithmic outcome. It's actually the magic due to a lasso penalty, right? If you look at the lasso regression, for example, there is a similar algorithm like this, okay, which has just the theta in here rather than this expected mean of the residual. Okay. All right. And now here is a graph showing you the kind of responses, effects. The experiment was designed as a pretty complex, fitting problem, where you have just a few sample, but a very high dimension, out of which 4 is actually a useful one, which is by the dotted curve in here, okay. And then you are going to, then the other 96 are actually, fake signals. Okay? And these are the actual form of the 4 true signal. And then you go through that fitting, and you can see, this is, the results. And the first 3, dimensions, the first 4 dimensions actually turn out a interesting function. Okay, this is the mean function, m, 1, 2, 3, 4. And starting from the 5th one, you see a boring function, which is 0, basically, of whatever input. Okay. All right. So the rest is just kind of mechanical progression. We're going to now add one more layer of sparsity, known as the group sparsity, where we start to use structural knowledges. Yeah.
Could you go back to Sparse?
Mm-hmm.
So for fj, is it a number or a function?
Fj is a number or a function. It is a function. When you plug in the number, it is becoming a number. You have the train. Remember our, kernel SVM and all that kind of thing.
So after it has to be evaluated for all the.
Yeah, it has to be evaluated. Yes. Yeah.
So why in this model there's no alpha here?
There is no alpha here.
Like in the additive models, there should be a y.
You can center the data. That's it.
Okay, I see.
Yeah. Yeah. Yeah, you can see in many places I've been sloppy. I neglect a constant or so on. I sometimes didn't normalize that, but that's something you can take care of, by a simple operation. Okay. All right. Any other questions? If not, let's see group sparsity. Okay. Again, things become very mechanical. The graphical knowledge of structure sparsity goes to here as well. If you have a group sparsity, you now are introducing something called a group norm. Okay, here is a L1, L2 norm where you are summing together the L2 norm of multiple groups. So basically, say you have a collection of dimensions, and here is a group, and that is a group. Then you made out of each group, a L2 penalty, which is this guy. Okay, and then you are going to sum them together as if you are summing together the L1 norms. L1 norm is about summing every term in their absolute value. Okay, so that's where you get here, and they are weighted by the square of the group size. Okay, and here I assume the groups are non-overlapping, meaning that one feature can be only in one of the groups, and this actually is a very simple selection scenario, which makes sure that once a particular feature is determined to be sparse, to be unweighted, then it should be doomed forever. It shouldn't actually have any chance to re-enter the game. Okay. So how to do that? I'm not going to actually even show the equation now. It's going to be still the soft thresholding technique that we talked about before. You are going to, basically decide whether a group is going to be sparse or not by checking this threshold function, whether it is below or above that. If it's below, then it will go to 0. Okay. And in the previous one, it is every single function will be tested like this. Right. And we define now the partial residual in the group unit, and then our update function will be almost the same as before, right? So you have still, of course, here the operator was replaced by Q. It is just the same as before. And then you have the soft thresholding function in here, as we had before. Okay. Okay, I think I don't have much to say. Any other questions? If you are curious about how this can be derived, you can, check the original paper. But the pipeline is the same, across all these different instances. And the good thing here is that you can pre-compute the smoother matrix, using the data, okay, and then you cycle through these iterations. The results actually is quite interesting. So here, I'm going to have a few groups like this. So you have 8 functions, okay, which are nonlinear. And I also made some difficult functions in here. You can see the functions are both determined by its shape and also the variance of the function, meaning that the data generated from these functions. And some small variance function is harder to tell because they actually are not varying too much across data. And then my data will be a combination of 8 features plus another 192 random features. And these random features had a correlation, okay, drawn from this thing. That's basically to define the group structure. Okay. And then here we can try, of course, the group structure is actually known. So you can try different algorithms. We have a group lasso, which is linear, okay. But respect the group. We have a span, which is nonlinear, but ignore the group knowledge. And causal, I forgot what that is. Maybe something in the middle. And the condition was tested on t equals to 0 and t equals to which is the strength of the group structure, how tightly they are coupled. And you can see that in both cases, the group span picked all the information, okay, all the true signals. And other algorithms start to miss a few. For example, this one missed the feature 3 and feature 7. Remember, these are the 2 features which are known to be difficult to pick. Right? So they fail at the right place. But these 2 algorithms are not bad. They actually picked everything already in here. But if you have a higher correlation structure, still, this algorithm pick every signal, but other algorithms, well, they are picking signal, but you can look at their fitness error, that they have a pretty bad fit in terms of the predictive accuracy. Here you have an even harder problem where you have an input dimension of 1,000, and then you start to see, the precision recall of the other functions drop. Even though they can pick the right feature, their fit is not very good. So the catch from here is that, from lasso, linear regression with structured sparsity, they can still help you to do feature selection, but they are not very good at making predictions. It is a poor fit of the nonlinear function. But if you use a nonlinear functional regression without structured sparsity, you can get a reasonable fit, but the feature selection power is not as good. You actually missed a few features. And this group span is a combination of the group lasso idea and the nonparametric regression idea to achieve the benefit from both sides. That's basically the message from this experiment. Okay, any questions so far? And these are basically the shape of the estimated function. And you can see they are, it's a pretty non-trivial, function. And the line here, of course, are the sample estimation of the function, which are built on the training examples. Okay? Therefore, they are not as smooth as the true one. And if you have a new point, you are going to interpolate somewhere in the middle and get a right estimation. Okay, finally, I have a last technique, which is the group span with overlapping groups. So here, the things become a little bit tricky. So when you have overlapping group penalty, that means a particular feature, for example, suppose I have the feature list from 1 to, say, 100. And there is this feature I, which may belong to this group, okay? And I may have a group penalty to push this whole group into 0. Why? Because the rest of the members are just not that interesting, and they are not predictive on the feature. But the same feature may also belong to another group, which actually says that it is quite interesting, right? And in the biology scenario, you can imagine a case where a particular gene is involved in different pathways. And in the context of one pathway, it is not really active. And, or maybe its effect is not utilized to generate a response. But then in another pathway, that same signal was actually utilized to generate a response. Okay? So in this case, you run into some complications, because what if I after my L1 penalization of the group sparsity, I push this block, this whole group to 0. Okay. Then if this function I is pushed to 0 in here, then it must be also 0 in the other group, right? Because the sparsity is basically the union of all the sparse groups, right? So that's actually a kind of a deficiency of a group sparsity. So what we want to do here is to actually now introduce a new technique to deal with overlapping groups, so that hopefully the sparsification can happen in a more differential fashion. So that's why a new technique called the latent functions is introduced. Basically, instead of just as you do here, penalizing a entire function in here, okay, I'm going to now redefine every function to be built on small latent functions. Okay, and then my penalty is going to be, for example, this one is defined on small latent function, h, okay, and then my function is going to be defined on little latent functions, okay, and then the latent functions can basically appear in different places, and if one group is shrink to 0, they still have a chance to become non-zero in another group. Okay, and I'm not going to show the equations, because this is once you are written here, it is just a group span problem with a slightly redefined group structure. Therefore, all the back-fitting algorithms I talked about before can be equally applied to here. Okay. All right, so that's an experiment to compare the group span with other approach, in this case with overlapping groups. And now you can see that, well, here the comparison is a little bit tricky, because we are not knowing the ground truth. So somehow in the literature, people would say if you pick a smaller amount of functions at the end of the day cleanly, you get a better results. So that's the case for 2 of the 3 pathways we actually examined, or 2 of the 3 scenarios we examined. But in this case, I don't know what's going on. We are still doing okay on the group span, but the other group plus 2 is also doing quite well. But you can see the span without the grouping structure is really not very good at doing feature selection. It's always giving you a lot of noisy feature discoveries. All right, so that's basically a slightly technical lecture on how you can apply the nonparametric and nonlinear technique into the regressional framework, and still being able to apply graph-induced structural sparsity. Okay, so with that, I think we see a convergence of many techniques before, like regression technique, kernel embedding, and graph-induced regularization and shrinkage. And with that, I'm going to close. And so on Friday, we're going to on Wednesday, we're going to see a slightly out of the context lecture on distributed MC. And then for next week, I have 2 final lectures on a fancier way of learning graphic models. So up to now, how many ways we have learned to learn graphic models, if you still remember? We know maximum likelihood estimation of graphic models. We know maximum conditional likelihood estimation of graphic models, right? Like CRF is to maximize conditional likelihood. We also learned Bayesian estimation of graphic models, right? So next week, I'm going to show you how to bring the technique of supported machines, which is built on margins of predictive error, into the learning of graphic models. I'm going to show you that the graphic models itself can be learned in a way that they maximize margin of prediction. And also, in the last lecture, I'm going to also show you the margin-based training and the likelihood-based training can also be combined together to learn a graphic model that is not only maximum likelihood, but also maximum margin. Okay? So with that, I would like to close the lecture so that you can see everything we learned at the end of the day will go together, and in a single framework, you will see likelihood, margin, kernel, and everything, okay, for learning a particular model. All right, see you next week then.